All right, so we're going to continue our discussion of SN2 reactions today. And when in the last lecture, we identified sort of 4 things that we need to think about when we're evaluating the, sort of feasibility or facility of an SN2 reaction. So substrate structure, nature of the leaving group, nature of the nucleophile, and solvent effects, okay? And we started talking about substrate structure. We'll do nature of the leaving group today, and then hopefully also items 3 and 4. And 3 and 4 need to be considered together. So the reactivity of a nucleophile sort of depends on the solvent. And this is where we'll start to see these parameters, get tangled up in one another. And so you need to be able to reason, your way through it. So I just want to drive home a point from the last class that might have gotten lost, given some of the questions that I've gotten. The smaller, the better for an SN2 substitution with regard to the substrate, okay? So methyl, always better than primary, always better than secondary, and we never do SN2 on a tertiary. And it's the same trend for the beta branching. So that's 1 carbon removed from the reacting center, but it's the same thing. Smaller, the better. The more beta branching you have, the slower the reactions get, okay? So okay, so methyl is greater than primary, is greater than secondary, and then no SN2 for tertiary. And then the second thing was the beta branching. So okay, so again, the position that the halide or the leaving group is attached to is alpha. The next position over is the beta. And so as you start to bulk up the beta position, you slow down the rate of SN2 displacement. And the extreme offender here is this one on the right, which, oops, what's going on there? We have a special name for that. We refer to that as neopentyl. So the neopentyl group is basically CH2-T-butyl. And so neopentyl substrates don't do SN2, even though to a first approximation they're primary. It seems like that should be a good substrate. That additional bulk at the beta position shuts down the reaction. So I showed you some Spartan images last time where we showed, the substrates bulking up as we increased the substitution. I wanted to run through that again, but with the line wedge drawings so that you could have that that representation as well. And so let me okay. So we'll just spend a couple minutes talking about the effect of beta substitution on the conformation of the molecules, and then also reactivity. And so the simplest sort of beta unsubstituted halide would be an ethyl derivative, so like ethyl bromide, for example. And what we want to do is think about the conformation of this molecule in 3 dimensions and what it, how that might interact or influence the approach of a nucleophile. And so this one's fairly straightforward. We can think back when we talked about conformation of ethane. We said that, okay, the staggered conformation is going to be more stable than the eclipsed because you minimize non-bonded interactions between the bonds. It's the same thing for bromoethane. So if I draw the structure like this, the lowest energy conformer is going to be this guy, where I've got everything in a staggered orientation, okay? It doesn't matter. You could put the bromine on the wedge, you could put the bromine on the hash, because the beta carbon doesn't have any other substituents than hydrogen. There's only one staggered conformer, okay? And so it's useful to look at this from a Newman projection. So I can redraw this, and we're going to redraw it looking with the, I just want to keep this same as I'm doing in my notes, looking from the beta carbon to the alpha, okay? And so here, I put the beta carbon in front. I've got one of my H's. We can label these A, B, C. HA is up, B is off to the right, C is off to the left. And then in the back, I've got my hydrogens, and my bromine is coming down, okay? And so that's simply a staggered conformation of bromoethane. And again, if you rotate the back carbon, looking at the Newman projection, rotate by 120 degrees, you get to the same conformer, just from a different perspective. So there's only one staggered conformation. And so this is the lowest energy conformer. And so if we think about what this looks like as a nucleophile approaches, we can go back to our line wedge diagram. Let me make this colored here. So as the nucleophile is coming in, okay, remember, the orbital constraints require backside attack. You have to come in from the back. And so 180 degrees with respect to the CBR bond. And so something like a trajectory, something like that, okay? And so what does that nucleophile see then as it comes in? Well, it's going to see the adjacent beta CH bond, right? And so if I use these green lines and I draw sort of overlapping curved lines, that's to indicate that there's a non-bonded interaction between the nucleophile and that hydrogen. So okay, so the lowest energy conformer of bromoethane is the staggered conformer. And the nucleophile, to displace that bromide, has to come in anti to the CBR bond. And so it's going to come in and see this adjacent beta hydrogen, right? Is that bad? Yes, it's bad. It's going to slow down the reaction, but it's not prohibitively bad. So this is still a primary substrate. I've just got a single carbon at the, or no branching at the beta position, a single carbon attached to the alpha carbon. And so these reactions are still quite facile, okay? But what we're going to do now to show the effects of this beta branching is iteratively substitute these beta hydrogens for methyl. So let's go to the next case would be bromopropane. Let me leave these out for now. Okay, so just building out by one carbon. I can draw a line wedge representation for this, and now I've got a couple choices because I now have this beta methyl substituent. I'm going to put it anti to the bromine. Okay, like that. And so if I replace that bromine with a methyl group, this would be anti-butane. And we remember from the butane discussions that the anti-conformer is the lowest in energy. It's the same thing here. Bromine is actually bigger than a methyl group. So this is, you know, even more like anti-butane than butane itself. And so this is going to be the lowest energy conformer. And if we, I'm just going to skip the Newman projection here, but if we think about what's happening as the nucleophile approaches, that nucleophile is going to see that methyl group now. Right? And so as the nucleophile is coming in, there's going to be this beta methyl that's hanging out there in space, and it's going to essentially present an electron cloud to the nucleophile, and that's going to repel the nucleophile. Okay, and so that conformer, although it is the lowest energy, is also going to be slow to react because of this non-bonding interaction. And so what can the substrate do? It can do a lot of things. One of the things it can do is rotate about that central carbon-carbon bond and get into a different type of conformer. And so I'm not going to go through, you know, the staggered to eclipsed. I'm just going to jump between the conformers that are important for the discussion here. But if you need to review those, I'd encourage you to look back at your earlier notes. And so what I'm going to do is 120-degree rotation here. So I'm going to skip through an eclipsed conformer and get to my next staggered conformer and hold the carbon on the right steady. And so to show that 120-degree rotation for the left-hand carbon, all I need to do is move the substituents by one position. So okay, so I can put my methyl group in front and then hydrogen in back and then hydrogen up. Okay. Does anyone want to venture a guess as to how the reactivity of this conformer might compare to the one that the anti one that we just discussed?
Would it be a higher reactivity?
Yeah, exactly. Hosanna?
Yeah.
Exactly. It'll be a higher reactivity because now, look what's happening. My nucleophile's coming in, right? And we're sort of back to that original scenario where, there's an interaction, but now it's back to being with a hydrogen, okay? But how would you rate, or how would you characterize this conformer with respect to the anti-conformer? More stable, less stable, the same? Does anyone want to take a stab at it?
Would it be less stable?
Yeah, why?
Because the methyl group and the bromine group are like closer together, and so they'll have like van der Waals repulsions.
Yeah, exactly, Helen. It's less stable. It's exactly right. And the reason is that they're closer together. Okay, another way to put that is this is a gauche conformation, right? So if we look at the Newman projection, and let me just draw the one in the back first, because that's easy. My bromine's going down. I've got a hydrogen up, a methyl group off to the right, and a hydrogen over, okay? And so this, remember gauche butane, we say gauche butane, is better than an eclipse conformation, but not as good as the anti, because you get this non-bonded interaction between the methyl groups. This is the gauche conformation of bromopropane, okay? So it's a different interaction, Br plus methyl, but the origin is the same. They're sort of in that staggered arrangement, but in kind of the same quadrant or third of the region of the molecule. So this is gauche, and if we go back and we say, okay, gauche butane's about 0.8, 0.9 kcals per mole higher in energy than anti-butane, we can say, it's probably about the same. So let's call it plus 0.9 kcals per mole. Okay. And if I'm remembering my math correctly, I think about 1 kcal is about 3 or 4 to 1 in terms of distribution. So you can imagine we've got about, let's just say roughly 20% of my bromopropane is sitting in this gauche conformation. There's another detail, which is that there is in fact a second gauche conformation, right? Where if I take this methyl group and move it over, rotate that front carbon by 120 degrees, I access a second gauche conformation. So maybe this is like 40% of the overall 40% of the population is kind of sitting in this higher energy conformer. Okay. What does that do? That decreases the overall rate. You can imagine, if I've got a conformer that's very slow to react, and I've got a conformer that's faster to react, but it's higher in energy than that slower reacting conformer, my molecule is going to have to take in some energy to get to that higher energy conformer so that it can react. And so that effectively increases the activation energy for the reaction. And if I go back here, trying to find the actual value that we said, shoot, on this, oh, here it is. Yeah. So we said that if bromoethane is 1, bromopropane is 0.4 in terms of the K rels. So a little sort of what we expected based on analysis. A little bit slower, not super slow, but I want you to understand the reason. So let me just go back and say it one more time. So in the bromoethane, lowest energy conformer is going to be a staggered conformer because there's only one substituent. You just have staggered and eclipsed are your only options. And so as the nucleophile comes in and attacks that the bromoethane from that staggered conformer, it sees a non-bonded interaction with the beta hydrogen, but it's relatively small. It doesn't cost it a lot, okay? If you go to bromopropane, now the conformational landscape gets a little more complicated. The lowest energy one is the anti-conformer, but that conformer shown here on the right in the middle is very slow to react because the nucleophile is going to be bumping into that methyl group as it comes in for backside attack. So what does it do? It reacts through a different conformer. Which conformer? In this case, a gauche conformer, slightly higher in energy, but that relieves some of these non-bonded interactions as the nucleophile approaches. And so, so the overall rate of reaction is smaller, but not by a whole lot. Okay. So again, this is what I'm saying. It's very fuzzy. You know what I mean? It's very fuzzy. And so you just kind of have to, just dive into it and process it and weigh these different factors. All right, so let's go up one more to sort of the double beta branched option, which would be this one. Okay, so now I got two methyls at the beta position. There's not a lot that this substrate can do in terms of its conformers. They're all going to be, essentially suffering from some sort of non-bonded interaction. So we can start by saying, all right, let's put a methyl group and a bromine anti to each other. That's always going to be a good place to begin. Okay, and then we can make a Newman projection for this one, looking from the left to the right. And so methyl group up, methyl group to the right, hydrogen to the left, and then in the back, hydrogen, hydrogen, bromine. Okay. And so we would also characterize this as a gauche conformer, right? So forgetting about this methyl group pointing up, this would be the gauche propane, bromopropane that we saw on the last slide. So this is a non-bonded interaction, okay? And so before we look at the nucleophile coming in, we can say, all right, let's ask the question, what happens if I start to rotate to look at other conformers? So let's take we'll hold the right-hand carbon fixed. We'll rotate the left-hand carbon by 120 degrees. And so when I do 120-degree rotation from the line wedge, all I need to do is transpose the substituents by one position. And so I'm going to move a methyl group here, a methyl group to the back, and then my hydrogen is up. Okay. And so now if we do the Newman projection, what do we got? We have basically hydrogen up, methyl to the right, methyl to the left, and then bromine down, hydrogen up, okay? And so this one, from the standpoint of conformational energy, is worse, right? Because I've got two gauche interactions in the molecule. So, but if we look at this from the perspective of the nucleophile is actually happier with this conformer, okay? And so if I'm going to redraw them over here. So if I'm the nucleophile and I'm coming in from this first sort of mono gauche conformer, right? I'm going to see that methyl group, and that's a problem. But if I come in through this higher energy gauche conformer that suffers from 2 gauche interactions, things look a little bit better for me, right? So now, if I'm the nucleophile, I'm coming in, but what am I hitting? I'm hitting a hydrogen, right? And so again, this looks a lot just like the bromoethane displacement. I have to access a high energy conformer, which is not good. So there's some overall, diminishment of the rate, but the reaction can still proceed. And this one we said the K-rel, if bromoethane is 1, this one was 0.03. Okay, so about 30-fold less reactive. And so basically up until, so just to summarize these 3 substrates, we're introducing these methyl groups at the beta position, but the substrate has kind of a low energy out. There's something it can do that doesn't cost it a ton of energy. That's rotate about that single bond, where I can basically make, if I'm the substrate, I can make myself look like bromoethane by presenting a hydrogen in the same direction and in the same plane as where the nucleophile approaches. Okay, so the rates get a little slower, but not by a lot. But then that's the limit, because now when I go to my neopentyl system, I have no good options. So I've got 3 methyl groups. I've got no beta hydrogens. Okay, I can draw this. There is, because we introduced symmetry back into the molecule now, there is only one staggered conformation, and that is like this. Right? And I can do a Newman projection if I want. Carbon on the left in the front, 3 methyl groups. Oh, okay, that's my Newman projection. And then if I'm a nucleophile, if I'm a nucleophile, what are my options? I have no good options, right? So I'm coming in here and I'm going to see a methyl group, and there's nothing the substrate can do to sort of help out. If I do a bond rotation, I just replace methyl with methyl, okay? And so there's no better conformer. They all are lousy. And so that's where the rate then plummets. So this actually, going from this substrate to the last one is actually, a good sort of controlled measure of, how much does actually a methyl group interfere with the rate of displacement. And so we said that the sort of the third substrate, the isobutyl, was about 0.03. This one is 10 to the minus 5. Okay, so the answer is the methyl group matters quite a bit. It causes a big problem, and there's nothing the substrate can do to help, get out of the way so that displacement can occur. Okay, so why did I go through all of this? Because when we get to elimination reactions, what I'm going to show you is that when these displacements slow down, what do we start to do? Well, we start to remove beta hydrogens, okay? And so, for example, this hydrogen, I'm getting a little bit ahead here, this hydrogen will get picked off by a base rather than the molecule suffering from displacement, and you'll eliminate bromide and make an alkene, okay? And all of that actually feeds right back to this conformational analysis. So, all right, let me pause there and ask if there's any questions on substrate effects in the SN2 reaction. Yeah, Ghana.
This is just like a point of clarification. So for the primary and secondary substrated beta carbons, do they have a higher reactivity than like the tertiary substrated beta carbon because they have the option to not have the methyl group interfere with the nucleophile?
Exactly.
Okay.
Yeah. There's a way it can get there, you know, by the bond rotation, to basically, you know, disguise itself and make it look like those methyl groups aren't there.
Okay.
Yeah, but you lose that in the bottom here with the neopentyl. Yeah.
Gotcha. Thank you.
Yeah. I can actually give you a if there's no other questions, I'll move on. But you know, just to give you a real life example, when I was a postdoc, I had to make neopentyl bromide, the molecule that's boxed there on the bottom left. You can get it from the chloride, and you displace with bromide. But that reaction occurs in conc HBr for about 3 weeks at reflux. Okay, and so that's what it takes to actually get that to go. So these effects are these effects are real. All right. So if there's no other questions on the substrate, the next one we're going to talk about are the leaving group effects. Okay, point 2. The good news here is this is relatively cut and dry. Okay, so it's important, and I'll call the leaving group LG. It's important to remember what's happening in the transformation. So my nucleophile's coming in, it's always has a lone pair, often has a negative charge. It's going to react with some substrate. I'm going to have a transition state. And I'm going to go on to product. So okay. And so the nucleophile, as I said, is often negatively charged. Okay. Regardless, even if it's neutral, as I approach this transition state, what am I doing? I'm starting to dump negative charge onto the leaving group. So negative charge builds on the leaving group in the transition state. Okay. And so remember, the transition state is the top of that reaction pathway. And so however high that is tells me how fast or slow the reaction is. Okay. And so if I have a leaving group that can accommodate negative charge, that's going to stabilize the transition state, going to decrease the magnitude of delta G double dagger, and the reactions will go faster. So I can for this one give you a general rule. Okay, so the more readily your X group can accommodate negative charge, faster the reaction. And generally what we say is that if the pKa of the conjugate acid of the leaving group is less than 0, so if the conjugate acid of the leaving group is a strong acid, generally X is a good leaving group. So
Sorry, Professor Herzog, quick question. That's meant to be a delta minus, not a delta plus, correct?
yeah, this is a delta minus. Thanks.
Okay, thank you.
Yeah, my handwriting. Yeah, delta minus. So if pK of HX is less than 0, then what we say is X minus is generally going to be a good leaving group. And if this is an important point, if the pKa is greater than 0, X minus is not a good leaving group. Okay. And so we can look at this if we just look at halides, for example. So displacement of methyl X with acetate, 1, 2, 3, 4, 5, 6, right? Gives me methyl acetate plus X minus. And so let's say X is going to be one of our halogens, bromine, chlorine, fluorine. The K rels for this reaction, so the relative rates of reaction are 3, 1, 0.01, and 0. Okay, and the pKa equals -10, -8, -6, and 3.2. So these are the pKas of the conjugate acids. Okay. So, these data basically support what I just told you. So the fastest reacting substrate is the one where the leaving group X minus is most stable. Another way to put that is that the conjugate acid of the leaving group is most acidic. Okay. And you can see this, again, this is, this chapter, we're always balancing different issues. You might say, wait, Herzog, but fluorine is so much more electronegative than iodine. Why is that, a bad leaving group? And the answer is it's not so much the electronegativity as it is how stable is that anion. So I minus is actually much more stable than F minus, okay? And that has to do with the much larger size of I. We talked a little bit about this. The negative charge is much more diffuse. So, point is you kind of have to know what sort of models and scales to rely on in these different reactions. And here we're really talking about pKa as being the guiding principle. Okay. But the good news is that, so 2 more points. So point 1 is that almost everything we're going to see is with a halide as a leaving group. There's a little bit at the end of the chapter where we talk about sulfonates, but they're very simple. For all intents and purposes, if you know this relative rate of reaction, you're basically good on the leaving group front. Okay. The second thing I want to say is that I put 0 here for F. Fluoride is just a terrible leaving group. Again, in spite what you might think because of its electronegativity, it's a very poor leaving group. Part of it is the fact is that, as I was saying, the stability of F minus is actually not, F minus is actually not that stable because the molecule is so compact, the charge is so localized. But also the other side of that is the CX bond strength. And so carbon-fluorine bond is very strong. There's no halogen bond that's stronger. The carbon iodine bond, by comparison, is very weak. It's about 60 kcals per mole, so much weaker. Okay. All right. So that's leaving groups, and then now we're going to get to the sticky stuff, which is the nature of the nucleophile. Okay. And we may not finish this today, but that's yeah, we definitely won't finish this today, but that's okay. Okay, and so I said 3 and 4 need to be considered together. So nature of the nucleophile and solvent effects, these are interrelated, and you can't really talk, about one without the other. And so what I want to start out by saying is that we're doing something that we probably shouldn't do, and it's a little dangerous. And so I need to explain clearly what we're doing so you understand what the limitations are. So we are mixing, when I say, better, lower pKa, better leaving group, I'm taking a thermodynamic property, which is acidity, how stable is, the conjugate base of a given acid, and I'm intermingling that with the kinetic property, which is a rate, how fast something happens. Leaving group ability is a kinetic property. Nucleophilicity is also a kinetic property. And so we can get some guidance from pKa's, but there are going to be spots where that analogy or that sort of framework doesn't help us, or it would give us the wrong answer. Okay. And the reason is that, strictly speaking, pKa is a thermodynamic property. Nucleophilicity, electrophilicity, leaving group ability, these are kinetic properties. And so sometimes they're in agreement and sometimes they aren't. Okay. And so there are kind of 4 things that we can think about here. I told you this is going to get sticky. So the first one is the basicity or the acidity of the conjugate acid of the nucleophile. So okay, so the pKa of the conjugate acid. Second thing is the solvent that we're using, and that's so important. The third is what we call polarizability. And then the fourth is just the outright size of the nucleophile. And by that, I mean not so much the atom itself that's bonding to carbon, but what comes along with that atom. What else is attached? All right, so the basicity analogy is useful if and only if, well, in 2 scenarios. So one is that if we're talking about atoms, if we're talking about nucleophiles where the reacting atom is the same, okay? So for example, hydroxide versus acetate versus water, those 3 species behaving as nucleophiles. If we think about the pKa of the conjugate acid, we're talking about 15. Does anybody know the pKa of acetic acid?
Isn't it like 3.5-ish?
Close, 4.72.
Oh.
Yeah. And then what's the pK of hydronium?
-2.
Yeah, about -2. Yeah. So hydroxide is the best nucleophile of this group. And water, neutral water, is the worst. And water is, you know, by all metrics, a lousy nucleophile. And so how can we think about this? Well, we know that the, you know, acidity, basicity, the lower the pKa, the more stable the conjugate base, right? The more stable the species. What is reacting atom is the, oh, sorry, is the same. Yeah. Okay, so the lower the pKa, the more stable the conjugate base. The corollary to that is the higher the pKa, the more reactive the conjugate base. And so water has a pK of 15, therefore hydroxide is very reactive. Acetic acid has a pK of 4.72, therefore acetate is less reactive, and hydronium has a pK of -2, and so water is basically is the least reactive of this bunch. So when the reacting atom is all the same, you don't need to sort of overthink it. You can say, okay, I'm just going to think about the pKa's. The one with the conjugate acid with the highest pKa is the best nucleophile. Okay, so nucleophile with conjugate acid with highest pKa is greatest nucleophile. Okay. So again, you gotta, yeah, just want to make it clear what we're doing. We're doing something we shouldn't do, which is we're crossing thermodynamics and kinetics, but it gets us to the right answer. It provides a simple way to think about it. And so we're going to do that here, but it's important that you keep that that sort of issue in mind as we move along here. Yeah. All right. Okay, so I'll just say one more thing and then we'll stop. And so the second place where we can use Bronsted basicity to rank order nucleophiles is if we're moving across the same row in a periodic table. So, oops, I lost my screen here. Here we go. Okay, so if we're moving across the same row in a periodic table, the more basic nucleophile will react the fastest. And so if you think about row 2, you have methyl minus is a better nucleophile than NH2 minus, which is a better nucleophile than hydroxide, which is a better nucleophile than fluoride. Okay, and so this is going to be the fastest reacting. This is the slowest. And if we go to pKa's, we can see that that tracks. And so we're at like approximately 50 for methane, 36 for ammonia, 16 for water, and 3.2 for fluoride. Okay, so the most basic, the most reactive conjugate base when you're comparing across a row is going to be the one that's the best nucleophile. Okay, but again, what we're doing is a no-no. We're crossing thermodynamics and kinetics, and so as soon as you want to compare two species from different rows, this does not hold. You can't just look at pKa. Okay, so there are two scenarios where we can use pKa to rank order nucleophilicity, and that's when we have the same reacting atom, so like series of oxygen-based nucleophiles, series of nitrogen-based nucleophiles, or when we're moving across a single row in the periodic table, which, you know, for all intents and purposes for us is going to be row 2. Okay, so that is where we can fall back on pKa values. And again, you need to be very careful and understand the limitations here, because the acidity, basicity are thermodynamic concepts, nucleophilicity, electrophilicity are kinetic concepts. All right, so Friday's lecture we'll start on the solvent effects, and I need to spend a little bit of time. For those of you that are reading ahead of time, you'll note that the text that's listed is a little bit ahead of where we are. I need to sort of balance that. I'll try to get to that this weekend. We're moving a little bit slower, but we actually have more lectures, so we'll get through all the material. Hopefully, it should be better than a normal semester. All right. All right. I'll close down and then rejoin the meeting in about 10 minutes after the video is finished processing. Have a good day, everyone.